To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
So, my dear children, in the earlier chapters, we discussed several theoretical parts and finally, we did the questions related to the nanotechnology lesson, right? So, we did some questions related to the textbook first of all. Now, within this chapter, we'll be discussing several extra questions related to the nanotechnology lesson, okay? So, my dear children, like in the previous lessons, first of all, we'll be discussing about several MCQ type questions related to the nanotechnology. Okay, so let's head on to see the first and foremost question then. So, number one given, nanotechnology was first introduced to the world by. So, the question is asking who was the first person, right? Who was the first person to introduce this nanotechnology thing to the world? You know that nanotechnology is the concept where we can use smaller molecules, right? Smaller molecules like, when you go to the molecular level, turning these smaller molecules into machines. That's the basic idea of nanotechnology, right? So, the first idea of turning these molecules into machines were given by, right? These things were given by several people, but however, the first and foremost idea of turning, right, this thing into a machine or else the tiny world that we cannot see, utilize these things in our day-to-day applications. So, the idea about these things, right, given to the world first by the great scientist Richard Feynman. So, he was given, right, he gave a certain kind of a speech. There's plenty of room at the bottom, right? So, on that speech, he first introduced this concept of nanotechnology. Actually, on that time, this field was even not named as the nanotechnology, but he was the first person to introduce this thing. He was the first person to lay down the idea of turning these smaller molecules into machines. So, he speculated that in the near future, these molecules can be turned into machines and even we can work with these things without any trouble, right? So, the idea of presenting, right, the idea of giving out this nanotechnology to the world first time was given by the great scientist Richard Feynman. So, our answer should be Richard Feynman. So, yes, in the response B, you can observe the correct answer, Richard Feynman, right? The next one given, the person who gave the kickstart to nanotechnology by writing the book Engines of Creation. So, the next one, my dear children, given, the engines of creation. So, Dr. Eric Drexler was the person who wrote down this book, right? After the speech given out by the Richard Feynman, right? Dr. Eric Drexler, he wrote a book which is called as the Engines of Creation, Upcoming World of Nanotechnology. So, by that book, he introduced this concept to all around the world, right? The concept of nanotechnology. So, from that, the nanotechnology and these experiments got a good kickstart, right? So, the person who wrote this book and gave out a kickstart to the nanotechnology field is Dr. Eric Drexler. So, let's go for the answer, Dr. Eric Drexler. Yes, can identify it in here. So, third response should be the answer, right? So, the person who gave the kickstart to nanotechnology by writing the book Engines of Creation was Dr. Eric Drexler, right? Then, the question number 3. So, image shows, so you are given with an image, So this shape is referred, now as you can see, it's like a twisted ladder, right? When you observe the shape, my dear children, it's like a twisted ladder. Okay, so this shape is referred as the double helical shape. Okay, the double helical structure. So you'll be learning about this double helical structure when you go further with your grades like grade 10 and 11. Okay, so this double helical structure was introduced by two scientists. Okay, so this structure is showing the structure of DNA, my dear children. Okay, the structure of DNA. So DNA structure is the one which is shown within this figure. This, remember this one, this is called as the double helical structure. Okay, like a twisted ladder. So go for the answer which contains the DNA structure. So image shows the DNA structure of organisms, right? The DNA structure of organisms. We don't know whether it is human or any other, but however, it's a structure of a DNA. So DNA structure, you know that it is in the nanoscale, my dear children, right? So when you check the DNA structure, it's very tiny. So it's even tinier than a cell, a typical cell. So therefore, my dear children, we won't be able to observe these things even from an optical microscope. We have to use the electron microscopes when observing these things, right? So DNA structure is the figure which is given under the question number 3. Then the question number 4. So once again you are given with an image, then you have to identify this thing. Okay. So as you can see here, it is in red color. Now if you are not given with a red color, now you know that when you are given with certain paper, you will be receiving most of the times, right, black and white images. So by that way, how can you identify the structure? You know that this is a cell. Okay, this cell is referred as a red blood cell, my dear children. So it's quite easy to identify a red blood cell because it is having a biconcave shape like this. It's having a biconcave shape like this. I mean, when you draw it, okay, when you draw it, it's like this. Okay, it's like this. Like this. It has a biconcave shape. Okay. So therefore, we can clearly identify without any trouble if you are given with a red blood cell, my dear children. Remember, it is always like this. It has a biconcave shape, my dear children, like this. Okay. Biconcave shape. So by just looking at this, you can clearly say that this is a red blood cell then. Okay, so I told you about the DNA structure, the twisted ladder. Then white blood cell is somewhat larger than this. And my dear children, when you draw a white blood cell, it contains a good nucleus at the center like this. So you can, without any trouble, you can clearly identify the structure of a white blood cell, right? Within the middle, you can identify a nucleus. But however, in red blood cells, you won't be able to identify a nucleus because the main aim of red blood cell is to carry and, is to bond oxygen and carry that oxygen all through our body. Okay. So therefore, it lacks a nucleus in order to provide a good surface area to bond oxygen. So therefore, right, it has a biconcave shape like this and there is no nucleus in it. Okay, so therefore, my dear children, the answer should be the red blood cell, first one. Okay, red blood cell. White blood cell is somewhat different than that. Okay, even when you take the size of a white blood cell, it is even greater than the size of a red blood cell, right? Remember, red blood cell has a biconcave shape. Right. Then next one, question number 5. Correct definition for nanotechnology science. Okay, nanotechnology science. The correct definition. It investigates the matter at the critical range on 1 to 100 nanometers. Making new things on incredibly small scale. Nano refers to something very small. It is the tiny micro world which we cannot see. So the correct definition, so you have to choose the most suitable answer in here. Sometimes there can be 2 or more answers, my dear children, that would go like, that would give like the same idea. Okay, so when choosing answers for the MCQ type questions, multiple choice questions, you should be very careful because you have to choose the most accurate and the correct one. So here the answers are given. It investigates the matter at the critical range of 1 to 100 nanometers. Next one given, making new things on incredibly small scale. Third one given, nano refers to something very small. Fourth one given, it is the tiny micro world which we cannot see. All of these things are correct, right? Nano world means the world which we cannot see. Actually, we can't see. Even from an optical microscope, we won't be able to observe the nanoscale. You have to use the electron microscope, the very tiny world. Next one, nano refers to something very small. Absolutely correct. Nano actually came from the Greek word, right? So it refers to something small. It is also correct, no problem in it. Number 3, see, making new things on an incredibly small scale. Once again correct, no? Turning molecules into machines. Molecules means the things which we cannot identify from our naked eye or from an optical microscope. So it is also correct. But however, my dear children, the most accurate definition for nanotechnology science is investigating matter at the critical range of 1 to 100 nanometers. This is the definition for nanotechnology. This is the definition for nanoscience. So our answer should be, the most accurate one should be, it investigates the matter at the critical range of 1 to 100 nanometers, right? Okay, so we know that it is a very small scale, we know that it is referring to a tiny world, and we know that here we are building machines at a tiny scale. But however, the correct definition should be what? It is going to investigate the properties of matter. It is going to investigate about the matter at the critical range of 1 to 100 nanometers. Okay, so the question number 6, my dear children. Biological cells such as red blood are about. So biological cells such as red blood cells are about 100 nanometers, 1 to 10 nanometers, 10 nanometers, 10,000 nanometers. So actually, my dear children, when you go for the scale like 1 to 100 nanometers, that's the nanoscale, no? Okay. So over there we are discussing about certain molecules. So my dear children, a cell is a kind of a thing which is composed of different kinds of molecules and contains different kinds of substances too. So each of these substances is made up with different kinds of molecules. So my dear children, definitely the size of the cells should be greater than 100 nanometers for sure. Okay, it should be greater than 100 nanometers for sure. Definitely should be greater than that. So all the answers which is given over here, 100, 10, 10, can be neglected for sure, because these things cannot be in the size of a red blood cell. So our possible answer should be what? The final one, 10,000 nanometers. How we took that thing? Because my dear children, now these things, when you check these things, you don't need to even remember out these things, my dear children. It's because by just looking at the answers, you can check the correct one, or you can get the correct answer. Just by looking at the answers, you can think and get. Okay? You will be needing only the thinking capacity and that ability. So always be rational. When you are getting an answer for a certain MCQ type question, always be rational and try to argue with the things which is given over here. We know that this nanotechnology refers to molecules which are at the tiny scale. So if they are referring to molecules, a cell is made up with, like several thousands kinds of structures or molecules, no? So definitely the size of the cell should be greater than that. Actually, it should be greater than the nanoscale level, which is 1 to 100 nanometers. So therefore, our answer should be, for this one, 10,000 nanometers. Okay, 10,000 nanometers. Right, then the next one. So question number 7. The instrument which used to observe nanoscale particles. The instrument which can be used to observe nanoscale particles. So you know that nanoscale particles are very tiny. Now tiny means actually those things are available in the scale of 1 to 100 nanometers. So we won't be able to observe these things by using an optical microscope. Optical microscope means, my dear children, here we are using the light. So simply it is called as light microscope. So optical microscope, light microscope, both the things are same. When you take the compound microscope, that is also the same thing, right? The same thing. Compound light microscope, same thing as the optical microscope, my dear children. So all of these three refers to the same one. So we won't be able to observe these things, nanoscale particles, by using optical microscopes or compound microscopes. We have to go for the electron microscopes. So there is no such thing which is given as an electron microscope, but however, this atomic force microscope, my dear children, that's a particular microscope which we can use to find or investigate about these nanoparticles, because it is a type of electron microscope. So our correct answer should be atomic force microscope. Atomic force microscope. AFMs, right? Okay, then the next one. Nanoscale is 1 billionth of a meter, 1 millionth of a meter, half of a meter, 10 millionth of a meter. So nanoscale is, my dear children, now when you take 1 nanometer, the nanoscale is going to refer, right? So nanoscale is like 1 billionth, not millionth, it should be billionth. So here we are discussing about the scale of 1 billionth of a meter, right? So in simple, we can say that 1 nanometer is equal to 1 over 1 billion, okay? Not million, but billions. That means, my dear children, there are 9 zeros. So 1 nanometer is equal to 1 over 1 billion of meters. So our correct answer should be 1 billionth of a meter, not million, but it should be billion, 1 billionth of a meter. Over there you can observe it. So this is the one we write it down like this by using the scientific notation. You take this one to the upper side. Before that, I'm going to convert into a power like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the one which we represent as 1 into 10 to the power negative 9 meters. So 1 nanometer means 1 billionth of a meter, my dear children. Okay. So the question number 9. Leaves with hydrophobic nature. So what is this hydrophobic nature, my dear children? Hydrophobic nature means when you pour some water into a certain surface, if that surface is hydrophobic, then water will not stick to the surface. To that particular surface, water will not stick into it, right? It will slide down gradually with ease. So we won't be able to observe the wetness in a surface, right? Because that hydrophobic nature or that water repelling nature in the surface is going to repel and turn down all the water molecules away from the surface. So the sticking ability is getting reduced over there. Okay. So that means, my dear children, right? Actually, it is going to happen because of the nanoparticles that can be seen around or seen on the surface. So this is observed within the lotus plant, okay, lotus plant leaf, and also some plant leaves like, taro yam or else colocasia, habarala, right? Within these leaves, we can observe this nature, the hydrophobic nature. And my dear children, in wings of some bugs, in wings of some butterflies. Okay, we can observe this nature, this hydrophobic nature. Okay, so my dear children, leaves with hydrophobic nature, like I said, lotus is correct. This is also referred to as the lotus effect. This hydrophobic nature is also referred to as lotus effect. It's because, my dear children, lotus leaves have this hydrophobic nature. Okay, then next one given, haberle. Once again correct. No, I told you about this haberle leaf like 1 minute ago. So that is also correct. Then next one given, colocasia. Once again correct. Right? Once again correct. It's a reference to Pteroiamo haberle. So all of these things are correct for the hydrophobic nature. Next one, lotus effect is once again referring to that thing, right? The previous question, it's a hydrophobic nature. Let's see. Having white color or colorful flowers. No, it's not referring to flowers or any other thing, right? So lotus effect means, my dear children, actually that is the hydrophobic nature of certain surfaces. Not sticking water on a certain surface because of having tiny nanoscale particles. So those nanoscale particles have the ability to repel water molecules and turn those things away from a certain surface. Right? So the next one given, having a hydrophobic nature on leaves. This is the answer. Having a hydrophobic nature on leaves. This is our answer, the lotus effect. Right? Having a leaf which can store water, having leaves and flowers that can stick water. It's not sticking but repelling. Okay? It's not sticking. Remember, it's not sticking. It means it's going to repel water. Okay? Turn down water to another different place. Right then. So, having a hydrophobic nature on leaves is the correct answer for the lotus effect. Question number 11. Nature made nanomaterial. Nature made nanomaterial, my dear children. Okay? Nature made nanomaterial. Remember. We know that graphene is a good example for nanomaterial. But however, that's man-made, an artificial thing. Usually, graphite is formed according to layers, or this graphite contains several layers of graphene. Okay. However, my dear children, graphene cannot be observed in our nature. Right? We have to separate graphene artificially from graphite. So graphene cannot be taken as a natural nanomaterial. But, my dear children, when you take a certain cell, right, the organelles contained within a cell. Organelles means a small structures which are located within the cell that helps in their biological activities. Like in simple, you know that our body contains different organs. In the same way, cells contain different organelles. Our body organs perform specific functions within the body. In the same way, organelles inside a cell perform specific functions needed for the survival of the cell. Like in simple, my dear children, when you take the metabolic activities, the control of metabolic activities, all the things, all the chemical reactions and all the other things related to the, right, related to all the other activities related to the human cell or else animal or whatever. These activities are controlled by the special organelle called the nucleus. And for their respiration, right, for the respiration of the cell, you know that respiration is quite important, right? Can you remember I told you about a special kind of a organelle which is called as the mitochondrion, right? So mitochondrion is very helpful in providing energy by doing the cellular respiration. So like that, there are different kinds of organelles contained within a cell. All of these things are performing a specific function, a specific metabolic activity within the cell. Like in the same way where when you take our body has different kinds of organs. So these organs are going to perform different kinds of functions to our body to ensure our survival. Okay. So in the same way, my dear children, within a cell, we can observe organelles. Specialty here is that a cell can be observed from an optical microscope. You know that. Even we observed cells from optical microscopes. Okay, during starting from grade 6 to up to now, right? However, my dear children, when you go deep inside the cells, at that time you can observe these organelles. So organelles are in the nanoscale. Cells are not in the nanoscale, but organelles are in the nanoscale. We can observe cells from optical microscopes without any trouble. But however, we won't be able to observe, right? There are some certain types of organelles which we can observe from the optical microscope. You will be learning about these things when you go further with your grades. Okay, but however, all the organelles cannot be observed from an electron microscope, my dear children. Right? All the organelles can be observed from an electron microscope, but however, all the organelles cannot be observed from an optical microscope, not from an electron microscope. From an electron microscope, we can observe anything. Anything means any organelle. Each and every organelle can be observed from an electron microscope. But however, when you take a certain optical microscope, right? Within an optical, by using an optical microscope, we can identify only the larger organelles like nucleus and cell walls and so on. Okay, there are like several organelles. Can you remember when we are doing the theoretical parts, we even discuss those things? So my dear children, even though the cells are not in the nanoscale, however, the organelles contained within the cell are in the nanoscale. Okay, remember, cells are not in the nanoscale, but organelles contained within the cells are in the nanoscale. So our answer should be, the correct answer should be organelles in a cell, because it is a nature-made nanomaterial. Naturally, those organelles are going to occur in our environment. Okay, when a cell is going to come out, right? When a cell is going to originate from a certain point or from a certain organism, we can clearly identify the organelles contained within them. So those things are natural. However, we can't take human cell. You know that polythene and graphene are artificial. The human cell is not in the, when you take a cell, cells are not in the nanoscale because those things are like somewhat larger. Even we discussed that in the previous questions. When you take a certain red blood cell, it is around 10,000 nanometers. So somewhat larger. Here we are investigating about 1 to 100 scale in nanometers. So therefore our answer should be organelles in a cell. Those things are nature-made nanomaterials. Next one. Nanoscale mainly focus from, this is really simple, my dear children. Even with the definition, we know that nanoscale is going to refer from 1 nanometer to 100 nanometer range. So go for the answer that has 1 to 100 nanometers. Yes, the first and foremost answer is correct. Nanoscale mainly focus from 1 to 100 nanometers. Okay, 1 to 100 nanometers. Within this scale, we can observe the molecules. Okay, within this scale, we can observe the molecules. Right. Then the next one, question number 13. Material which demonstrate a range of colors depending on the size and the shape at the nanoscale. Copper, gold, carbon, graphene. So material which demonstrate a range of colors depending on the size and shape at the nanoscale. So here, my dear children, you know that when changing the A to B ratio, you know that when you take any kind of material, when you go for the nanoscale of it, even though the volume is not changing, the surface area is getting changed. So therefore, different kinds of specific properties like, special kinds of physical and chemical properties could be observed. Okay, so here the question is asking, according to the according to a range of colors, right? Now, or else according to a size and the shape of the nanoscale particles, a range of colors can be observed within this material. You have been asked, what is that material? So you know that gold is a certain substance which is an inert in the nature, but however, it is very active, dramatically reactive in nanoscale, right? So my dear children, because of that reactivity, gold is the one which is going to demonstrate these different colors. So our answer should be the material which demonstrates a range of colors depending on the size and the shape in the nanoscale. This is only in the nanoscale, not in normal environment. I mean, like, not in the macro scale, right? So our answer should be gold, as it is very reactive in the nanoscale level. Next one. These nanomaterials can be converted into resistance-free conducting materials. Resistance-free conducting materials. Copper, gold, carbon and graphene. Once again, the same things given. So, you know that graphene, carbon, copper, gold, all of these things are conductors. And even we discussed that in the previous one, gold is going to behave, I mean, like, it's going to show some unnatural, when you take gold in normal environment, right? Gold is going to show different kinds of properties. However, though way more different properties can be observed if you go for the nanoscale of gold because of change in the reactivity. Okay, but however, my dear children, resistance free. Okay, resistance free. Resistance means the obstacle given against the flow of current. Resistance free nanomaterials can be observed, right? So these nanomaterials can be converted to resistance free conducting materials. So carbon and graphene, actually carbon is the correct answer. Carbon is the correct answer for this one. Okay, you might go for the carbon for sure, I know that. But however, my dear children, you have to choose the most accurate answer in here. In carbon also, graphite is the one which is conducting electricity. Carbon rods means graphite rods. So over there we use graphene as the substance to conduct electricity. So graphene can be converted into resistance-free conducting material, right? So our most accurate answer, carbon is the one correct. Carbon is correct for this answer, for this question. But however, you have to choose the most accurate answer. So our correct, most accurate answer should be graphene. Because graphite is the form of carbon that can conduct electricity. Within graphite, we can observe graphene. Graphene is the one can be converted into resistance-free conducting material, right? When you go for the nanoscale, okay? So our correct answer should be graphene. Next one, question number 15. The main reason for changes in physical and chemical properties in nanoscale particles. So we discussed that thing in the previous question. Can you remember? I told you that the dramatical change in these properties, like having special kinds of chemical and physical properties, these changes are occurred within the substances because of changing A to V ratio. That means even though the volume is keep getting constant, right, within the structures, okay, when you go for the nanoscale, the area, surface area is getting dramatically increased. Okay, so due to increasement of surface area of particles, here we can observe different kinds of special properties. Special specific properties can be observed. Okay, so go for the answer due to increasement of surface area. So increase in surface area, yes my dear children, this should be the answer. Increase in surface area. Let's see the other ones as well. Increase in volume. Not the volume is not going to increase. Volume is going to be same, my dear children, because we are using the same material in here. Next one, decrease in volume. That is incorrect. Like I said, there is no change in the volume. Decrease in surface area. That is also incorrect, because like I said, when the particles are getting smaller, the surface area is getting increased, not decreased, right? Okay. Question number 16. Type of a machine that can be used to observe nanoparticle. Type of a machine that can be used to observe nanoparticles. So can you remember, we have come across with this kind of a question in previously also. So over there we discussed about that special kind of an electron microscope which is called as the atomic force microscope. A special kind of an electron microscope. So we use the electron microscopes in order to observe, my dear children, in order to observe these nanoscale particles. Let's go for the answers. We'll check whether there are any electron microscopes. So the first one, atomic force microscopes. Earlier also we took this thing as the correct answer. So atomic force microscope is the correct one. Okay, it's a correct one. Next one, scanning tunneling microscope. Once again, this is also correct. Can you remember? There were 3 types of electron microscope: scanning tunneling microscopes, atomic force microscopes, and, my dear children, scanning probe microscopes. All of these 3 instruments are in the category of electron microscopes. So all of these instruments can be used to observe, right, nanoparticles. So all of these things are correct, my dear children. The 3 main types of nano, right, 3 main types of electron microscopes which can be used to observe nanoparticles. Okay, right, so all are correct for the question number 16. Next one, substance that shows allotropy. Right, the allotropy. What is allotropy? Allotropy means, my dear children, the polymorphic nature. Then what do you mean by the polymorphic nature then? The polymorphic nature means if you take a certain substance or else a certain element, if that element is available as different substances, even though the same substance, right, even though it is made up with same substance, if there are different, forms of or different kinds of things available in the environment, right, same substance but there are different forms in it, then that particular substance is a substance that shows the allotropy, or it contains polymorphic structures, right? So when you take carbon, my dear children, carbon is a good example for a polymorph. Carbon is available as diamond, which is very expensive. It has a good glitterness, right? It has a good refractive index, and it is like a glass. It has a glassy nature and it's very hard. Properties of diamond. Carbon is also available as coal. Charcoal, a small bit of a brittle substance, black in color, lightweight, right? When you can crush it by your hand just by giving out a very simple force, as it is brittle, and it contains different small pores, right? Smaller pores within the structure. So this charcoal can be used as a purificative substance or purifying substance, right? Carbon, right? Charcoal is also made up with carbon. So carbon is available as diamond, carbon is available as charcoal, carbon is also available as another crystalline substance, which is called as the graphite. So graphite has a, somewhat slimy. That means it can slide past each other. It can slide, right? So it has a slimy nature. Then, my dear children, right? When you take graphite also made up with carbon, and the specialty here is that Graphite is way more different than charcoal. Graphite is having a crystalline structure. That means it is arranged as like a crystal, same as diamond. However, not that much hard as diamond, but harder than charcoal. Okay. Diamond is in, it has a glassy, somewhat glittery nature. But however, even though graphite is also a crystalline substance, we won't be able to observe that glassy nature in graphite. It has a black color, black nature. So I took 3 examples, right, of different forms of carbon. All of these forms are made up with carbon, but however, they have different properties. These kinds of structures are referred as polymorphs or allotropy. Okay, remember my dear children, allotropy means different forms can be observed, but however, that thing is made up with same substance. All of these things are made up with same substance, but different forms. That means they have different properties. Okay, so go for the answer that has carbon. Oh, carbon is there. Then my dear children, so I told you about the carbon. No, carbon is correct. So you might go for the carbon. No, not carbon. Actually, there are other substances that shows the allotropy. Sulfur is also showing allotropy because sulfur can be observed as 2 different forms, as white color sulfur and yellow color sulfur. So even though they are available as 2 different forms, right? I mean, like the color is changed, right? One kind of a sulfur can be observed within yellow color and the other is in white color. Color is changed. The chemical properties and the physical properties are changed. But however, both the substances are made up with sulfur. So sulfur is also showing allotropy, same as the phosphorus. Can you remember when we are discussing the theory parts, I told you that white and red phosphorus can be observed, right, in our nature. Red phosphorus even can be observed within the surfaces of matchboxes. That red color surface on the matchbox is, that particular thing is made by utilizing red color phosphorus. So sulfur, phosphorus and this carbon are all examples for allotropy forms. Okay, so all of these substances show allotropy. So our answer should be above word. Next one, polymorphs of carbon. So it's very simple, my dear children. The 2 polymorphs, there are several polymorphs of carbon like charcoal, coal, graphite, diamond. Like that, there are different forms. But however, the main 2 forms that we are going to study within the O-level structure is about diamond and graphite. There are other forms as well, right, like charcoal and so on, but however, we are mainly focusing about within these 2, right, or else these 2 main ones, right. So our answer should be graphite and diamond. So let's go for the answer, graphite and diamond. Yes, in C you can observe it, graphite and diamond. Okay, right. Question number 19. The structure shows, so when you go for the structure, this is one structure, one polymorphic structure of carbon. As you can see, here the particles are well orderly arranged, and if you take one particular section like this, there are 4 carbon atoms, 1, 2, 3, 4, and there are 4 bonds within one carbon atom, 1, 2, 3, 4. So can you remember, my dear children, if you take a certain structure, if one carbon atom is bonded with 4 nearby carbon atoms, then that structure is going to be very strong. Such a strong that it is going to be the hardest substance, hardest naturally occurring substance in the whole wide world. So this is, my dear children, diamond, not graphite. It should be diamond. Okay, it's very simple to identify. You take one particular atom, carbon atom, from the middle or else from a corner like that, then count the number of bonds. Each straight line is going to represent one bond. So if it is bonded with 4 nearby carbon atoms, then it is diamond. As the bonds are somewhat stronger, it's going to be diamond. If it is bonded with only 3 nearby carbon atoms, then it is graphite. Okay, somewhat, less denser and somewhat less stronger than diamond, as it is having 3 bonds. Right. Next one. Number of bonds in an atom of above structure is very simple. In an atom in the above structure, the number of bonds are 4, my dear children. There are 4 bonds, right, in an atom of the above structure. Can you see? I have even counted 1, 2, 3, 4. When you take the atom over here, there are 4 bonds. Around it, there are 4 bonds. So 4 nearby carbon atoms bonds together in forming the crystalline form of diamond. Okay. Next one, question number 21. Polymorph of carbon which arranged as different layers. Polymorph of carbon which arranged as different layers. So there can be different layers, my dear children. There are different layers. So what is the polymorph of carbon that is arranged as different layers? Can you remember? We even discussed that thing like 2 minutes ago, right? If they are arranged as a layer with weak bonds, that means, my dear children, this is referring to graphite. Graphite is the substance which is arranged as layers. Graphite. So go for the answer that contains graphite. Not diamond, because diamond is way more hard than that. When you take the structure of diamond in the previous question, you can observe this. See, this is the structure of diamond. Diamond is not having layers, right? There are well-fashioned and well-ordered bonds and atoms can be observed within the structure of diamond. There are no any layers in it. However, when you go for the graphite, my dear children, graphite can be observed as different layers, right? Different graphene layers, right? So therefore, my dear children, the layers are arranged in graphite, okay? Graphite. Question number 22. The figure shows the structure of a, see, now it is going to show, actually it is also referring to the previous question. Can you remember over there we discussed about the layer thing? So graphite is made up with layers. One particular layer contained within graphite is referred as a graphene layer. So this is a graphene layer. Like this, if these layers are getting collected, a large number of layers like this, if they are getting collected to each other, such a structure is the one which is referred as a graphite structure. Graphite structure. So this particular layer shows graphene, my dear children, a graphene layer. Okay. So graphene means one single layer from the structure of graphite. One single layer from the structure of graphite. What is the specialty in graphene? Graphene has several specialties. Even though this is very tiny and thin, the strength of graphene is very high, and it is also going to show, like in the nanoscale, some resistance-free ability of conducting electricity. So graphene is very important for us in making different kinds of consumer goods and also in electronic science. Okay. So the figure shows the structure of a graphene layer. Okay. Not graphite, remember, it's a graphene layer. Just one single layer, no. So it's a graphene layer. Right? A graphene layer. Right? Okay. Question number 23. Now over there you can observe another structure. So the structure shows, now if they are arranged as layers like this, see, now here you can observe layers, my dear children. As you can see here, this is one single layer, this one. See, this is another layer and this is another layer. So just by looking at this structure, you can come into a direct conclusion that this is definitely graphite. Without any trouble, just by looking at it, we can get the answer. See, it's very simple. See the structure? Arranged as layers, see? Arranged as layers, there are 3 layers, 1, 2 and 3. And between the layers, by using broken lines, weaker bonds are being shown. So definitely this is a graphite layer, my dear children. So this is the structure of graphite. The structure of graphite. Then the other specialty. Been asked in the second question, see, related to this one. The number of bonds in an atom of the above structure. Number of bonds in the above structure. When you take one single atom, let's count the number of bonds. So when you take atom over here, it is going to show a bond like this and a bond like that and another bond like this. See, so only there are 3 bonds. There are only 3 bonds, right? There are only 3 bonds. So each and every carbon atom, see, it has 3 bonds, right? Nearby 3, right? Nearby 3. So these are weaker, the ones which are between the layers, those bonds are very weak. How? Okay, those bonds are very weak. So in graphite, my dear children, mainly this atom is going to create, one carbon atom is going to create mainly 3 bonds. Okay, 3 bonds, not 4 but 3. That's right. So our answer should be 3 bonds. Actually, that is the reason for the having that electrical conductivity. You know that to conduct electricity, there should be free moving ions or electrons. Can you remember when we are discussing the electrolysis lesson, we discussed that in order to flow electricity from a solution, there should be mobile ions in it. That means free moving ions, mobile ions. When you take a certain metal can also conduct electricity because it contains electrons which can be freely movable. Okay, electrons inside a metal has the ability to move freely. So therefore, metals also can conduct electricity. Okay, each and every metal has the ability to conduct electricity. Then how come the graphite is going to have that ability of electrical conductivity? Because, my dear children, when you take graphite, usually you know that graphite is made up with carbon atoms, no? In the, when you take the carbon atom, in the carbon atom, usually there are 4 electrons at the last level. Can you remember when we are discussing about the atomic structure, we discussed about the electron cloud, right? So within the electron cloud, my dear children, in carbon, okay, this is just a simple brief. You will be learning about these things in detail when you go further with like grade 10 and 11. Just a brief. So within the electron cloud of the carbon, there are 4 electrons. There are 4 electrons. Okay. So, however, these 4 electrons, right? All 4 electrons are not getting bonded in graphite. 1 electron is left behind the structure without making a bond. Now that electron has the ability to move freely within the structure of graphite. That means that particular electron which is left over without making a bond, that electron is not going to participate in making bonds. So it's going to left behind within the structure. So therefore graphite has the ability to conduct electricity, because that lone electron has the ability to, freely move within the structure of graphite. So graphite is going to conduct electricity. Okay, graphite is going to conduct electricity. Just a brief how graphite can conduct electricity. You know that then diamond can't. Why is that? Because all 4 electrons in diamond, okay, all 4 electrons in diamond has been utilized in making bonds. So therefore, diamond will never going to conduct electricity, even though those things are made up with carbon. Okay, right then. Question number 25. Thickness of graphene is about. So, thickness of graphene, my dear children. Graphene, when you take graphene, let me take you to the previous slide for a moment. This is graphene. Like I said, I told you that graphene is very, right? It has a very thin layer like this. However, the strength of graphene is very high. This layer is around, the question is being asked, how much is the thickness within this layer? So let's go for the answers now. 1 nanometer, 100 nanometer, 0.5, 5 nanometer. Actually, the thickness of graphene is about 0.5 nanometers. 0.5 nanometers. See, very thin. It's going to go even beyond the scale of nano. Okay, even more smaller than the nanoscale. Usually nanoscale refers to 1 to 100, no. However, the thickness of graphene is like 0.5, half of a nanometer. Okay, very thin, very, very thin. However, the strength is going to be very high. Okay, so this is the answer then. 25th, 0.5 nanometers. Next one. SWCNT stands for. SWCNT, single wall carbon nanotube, right? Single wall carbon nanotube. So you know that graphene has the ability, right? Graphene has the ability to flex here and there. It is very flexible. So it's very convenient to use. It's very easy to use. And even we can utilize these things in making different shapes, right? Even though it is very strong, it is very flexible, my dear children. Graphene is very flexible. So you can take a graphene layer and you can, turn it into a tube kind of a structure. So that kind of a tube kind of a structure, which is made by a layer of graphene, is referred as a carbon nanotube. According to the number of tubes contained within the structure, there can be single wall carbon nanotubes and multi-wall carbon nanotubes. Single wall means only just one single layer of carbon. Graphene layer. That's it. So our answer should be, my dear children, SWCNT means single wall carbon nanotube, not carbon nitrogen tube. There is nothing like that. Single wall carbon nanotube. That should be the answer. Okay, single wall carbon nanotube. It's not single wall carbon tube. N is there. N means nanotube. Single wall carbon nanotube. SWCNT. Question number 27. The figure shows. Now within this figure, there is another structure given. So within this structure, can you see there are several walls, my dear children, several tubes. Okay, there are several tubes. Can you remember about that single wall carbon nanotube? So in the same way, there are several tubes in here. So this is a multi-wall carbon nanotube. Multi-wall carbon nanotube, my dear children. So go for the answer that has multi-wall carbon nanotube. Carbon nitrogen tube, incorrect. Single wall carbon tube, incorrect, as there are several. Multi-wall carbon nitrogen tube, incorrect. Multi-wall carbon nanotube, yes, this should be the answer. It's not nitrogen. Now remember, it's a nanotube. Huh? Okay. Multi-wall carbon nanotube. Next one. Molecule which consists of about 60 carbon atoms arranged in the shape of a football. Like football kind of a structure. Can you remember? In our laboratory, we prepared the structure, right? We use the graphene layer and we're going to fold it down, right? Actually, scientists are the ones who are going to do it. We won't be able to do that kind of a thing in our normal laboratories. So we can take, or scientists can take these graphene layers, then by fold it into a shape of a football, like a ball, we can create this structure. So this is called as the fullerene, right? Go for the answer. We are fullerene. Yes, fullerene. It's not multi-wall, it's not single wall, it's not a graphene layer in the shape of a football, like 60 carbon atoms are arranged. That is fullerene, right? Fullerene. Next one. Uses of active carbon. So what is active carbon, my dear children? Active carbon is a structure, right? Or else simply we can say that this is the charcoal, right? Active carbon, charcoal. So you know the charcoal has the purification ability. It's because it has small pores, very small pores. These pores are in the nanoscale actually. So it has the ability to absorb certain things. Okay. When you take the right surface area of this active carbon, surface area is very high. Surface area of active carbon is going to be very high. Okay. As it has very high surface area, it has the ability to absorb certain substances into it. So therefore, my dear children, active carbon is used to make medicine. To make medicine, you know, to absorb certain things, active carbon is being used. That is correct. Next one. To make cosmetics, definitely active carbon is being used, because to remove all the substances like dirt and other stuff on the face. Can you remember a black kind of a mask is being applied on our faces? Then we leave it for drying for about few minutes. Then we can remove it. By that way, we can remove all the dirt and other kinds of foreign substances which placed on our face. So it is used in cosmetic industry, right? This active carbon is way more used in the cosmetic industry, like in making those kinds of masks, clearing masks. Then when you take face wash, right, and in application of different kinds of skin creams, the manufacturers are going to use this active carbon, my dear children. Okay, so here making cosmetic is correct use of active carbon. Then next one, in electronics. In electronic also we use this active carbon. In electronic also we use this active carbon. So all of these things are correct, my dear children. All of these things, right? Next one. 1 gram of active carbon has a surface area about. Now, like I said, it has a very high surface area. When you take 1 gram of active carbon, it has a surface area around 3000 square meters. Around 3000 square meters. Can you remember? It's equal to like this. When you take a certain ground that has a length of 30 meters and that has a breadth of 10 meters, then the area of this surface is equal to 30 into 10, right? Just 300. See, this is just a simple ground, no, 30 meters length, 10 meters breadth. So 300 square meters. So 10 times of this one, if you take 10 times of this ground, the surface area is equal to, right, that surface area is equal to 1 gram of active carbon surface area. 1 gram, just 1 gram of active carbon, okay, contains about 10 times of surface area like this structure or this playground, which is 30 meters in length and 10 meters in breadth. Okay, so 3000, about 3000, right, about 3000 square meters can be observed, right, in 1 gram of active carbon, my dear children. Okay, next one, question number 31. Figure shows the structure of, now the figure. So we were discussing about active carbon in the previous questions. So this is that structure of active carbon, my dear children. As you can see here, active carbon contains different pores or smaller holes in the nanoscale. So these holes are the ones that has the ability to attract, or when some certain thing is going to fall, it's going to go deep within these pores and going to stick on there, right? So this is the structure of active carbon then. So go for the answer that has the active carbon, not diamond, not graphite, active carbon, my dear children. That is the correct answer, right? Active carbon. So remember, active carbon is like this. It contains several pores or holes, right? So those holes has the ability, or those pores has the ability to absorb or to attract foreign substances like dirt and smaller particles into these pores. So by that way, the cleansing ability can be observed within the active carbon. Okay, cleansing ability or the cleaning ability, self-cleaning ability. Next one, HDL stands for high density lipids, high density lipoproteins, high density proteins, higher down lipids. So HDL, can you remember when we are discussing about cholesterol? Okay, a favorable cholesterol is HDL. HDL means lipoproteins. Actually here, you know that lipids are not getting dissolved within water. So in order to, as a remedy, our body is going to combine lipids with protein and transport these things as lipoproteins. Okay, so there are two types of lipoproteins as HDL and LDL. HDL, LDL, high density lipoproteins, low density lipoproteins. So HDL means, my dear children, high density lipoproteins. Those are the favorable cholesterol types or lipoprotein types in our body. So the correct answer for HDL is high density lipoproteins, not lipids. High density lipoproteins. High density lipoproteins. HDL, high density lipoproteins. Next one, 33. Favorable lipid compound to body. HDL, LDL, animal fat, plant fat. So lipid compound, fat is a lipid compound, we know that. Animal fat, plant fat. Plant fat, will ignore about animal fat. We know that, I think we have heard that animal fat is somewhat unfavorable for our body. Okay, there are some certain kinds of animal fat. Those animal fat, if you take it in a larger scale, then those things are unfavorable for our body. But however, we have learned that, right? We have learned, and also we have some kind of an aware that this plant fat is not that much, right? That not that much dangerous to our body, as they are made up with plants. Plant fat are not that much unfavorable for our body. But however, my dear children, there are some certain types of plant fats, okay, which is going to be unfavorable for our body if you use them in greater extent. Like for an example, if you take HDL, right? HTL, if a certain plant item is or plant fat is containing large amount of HTL, then my dear children, it's not going to be an issue. Then that plant fat is somewhat favorable for our body. But however, if it is going to contain large amount of LDL, that means low density lipoproteins, then that plant fat is going to be terrible for our body. There are some certain plant fats which is getting converted to LDL when high temperatures are given for those fats. Sometimes when using these things over and over once again and again, HDL contained within that plant fat is getting converted into LDL. Okay. So plant fat are usually okay, but however, that depends according to the amount of HDL and LDL levels. So we can't come into a direct conclusion that plant fat are okay. However, my dear children, HDL, that means high density lipoproteins, are somewhat favorable for our body. Those things are favorable for our body. Okay, even we have learned this thing within this lesson part. Can you remember? LDL, low density lipoproteins, can be converted into HDL lipoproteins by using nanotechnology. It's because HDL is favorable for our body. So HDL should be the correct answer. Don't go for the plant fat, because we don't know the concentration between HDL and LDL contained within that plant fat item. Okay. So the correct answer should be HDL. HDL is okay, no problem. Next one. Widely used nanomaterials in electronics has high resistance, low resistance, resistance-free nature, extremely high resistance. So widely used nanomaterials in electronics. Now in electronics, my dear children, we use these nanomaterials widely. I mean, like, we use these things in a greater extent, right? These nanomaterials, because it has very, very low resistance. Actually, low means low as resistance free. Okay, low as resistance free, not high, right? If the resistance is high, then it's going to be terrible, my dear children, because obstacle given against the flow of electric current is the resistance. So if high obstacle is given, then it's very difficult to handle these electronic items, as the loss of electrical energy is going to be very high. So therefore, in electrical field, it's very important to have less amount of resistance. Okay, so nanomaterials of carbon, they have the ability to conduct electricity in a resistance free mode. So therefore, my dear children, low resistance is correct, but however, the most accurate one would be resistance free nature. So widely used nanomaterials in electronic has the ability of resistance free conduction of electricity, right? Next one, question number 35. The size of an ordinary transistor is about. Ordinary transistor, not a modern one, but an ordinary transistor. You know that modern transistors are like now in 5 to 7 nanometers. Then like in 2015, like in that kind of range, right? It was reduced, right? First of all, it was reduced up to 15 to 30 nanometers, then 7 to 40 nanometers, then now up now in these days, the size of the transistor now in these days, like up to 5 nanometers, even more smaller than that, right? However, the size of an ordinary transistor, where at the beginning was around, right, how much? 130 to 250 nanometers. At the beginning, that means when you go for the old fathers of transistors, these things are called as vacuum tubes. Those things are even can be held in our hand, my dear children. Those things are very large. However, the size of that thing reduced with producing an ordinary transistor up to how much? 130 to 250 nanometers. Then it was even reduced up to 15 to 30, then even reduced up to 7 nanometers. Nowadays, actually we use like 5 nanometer kind of transistors. So ordinary transistor is about 130 to 250 nanometers. Okay, ordinary transistor. Right. Next one, not a use of nanotechnology. Not a use, okay, not a use. To make speedy minute transistors. It's a use, right? It's correct, no problem. It's a good use. To make speedy and minute transistors, it is correct. Making very thin solar panels. It is also a use, no? To make very thin and flexible solar panels, we use these things, right? We use the technology of nanoparticles. That is correct. In making flexible solar panels, once again correct. Can you remember about the graphene, my dear children? Over there we use, right? The flexibility. So to make flexible solar panels, we can utilize the nanotechnology. It's correct. Making very large size transistors. What's the point of making a very large size transistor, right? Our aim should be to minimize the size, no? Now in the previous question we discussed that size of the transistor now has been reduced like up to 7 nanometers, starting from 130 to 250. So we are developing a technology. Actually we are going to reduce the size of transistors to make our work easy, to make our electronic world quite easy. So in here they are saying that now making very large transistors. So what's the point of making it large? There's no point of it. I mean, we actually don't need a nanotechnology to prepare, like very large transistors, right? So that should be our answer. To make large transistors, we don't need nanotechnology. What for? Right? So this is the answer. This is not a use of nanotechnology. Question number 37. Figure shows, it's very simple, my dear children. This is the Institute of Nanotechnology. The Institute of Nanotechnology. Where? In Sri Lanka. Of course, in Sri Lanka. Not in America, not in China. This is the Sri Lankan Institute of Nanotechnology, which is located at Pitipana, Homagama area. Okay, so our answer should be, the figure shows Sri Lanka Institute of Nanotechnology, right? It's not the World Nanotech Center, it's not the American Nanotechnology Center, it's not the Chinese Nanotech Center, it's the Sri Lanka Institute of Nanotechnology, which is located at Homagama, not in Colombo, but in Homagama. Okay, Pitipana, Homagama. You can get more details about the nanotechnology if you can contact the center, right? New trends related to the nanotechnology and all the other stuff, basic stuff can be taken from this facility if you contact this facility, right? In Sri Lanka also there is a center, nanotechnology center. This is that center, my dear children, which is located in Pitipana, Homagama area, the Sri Lankan Institute of Nanotechnology. Right. Question number 39 then. Select the incorrect statement. So you have to select the incorrect one, my dear children. Let's see. Nanotechnology cannot be used to cure cancers. Nanotechnology cannot be used to cure cancers. Incorrect. When we are starting the lesson part, first and foremost, we discussed that when we are going to the future, I mean like in our near future, there would be a time that our society is going to be free of cancers. Because with the development of the nanotechnology, nanobots or nanomolecular robots are being now, actually those molecular robots are now under construction. So these molecular robots have the ability to find and destroy cancer cells in our body. So we will hope that in our upcoming future, we'll hope that this is to become this kind of a structure, this kind of a science will become a reality, so that we can save millions of lives. Okay, so it's a very good example for the development of nanotechnology and a pretty good use of nanotechnology as well, right? In our future, not in nowadays, but however in future there is a possibility to create these kinds of molecules which can destroy cancer cells. So it can be used to cure cancer cells, my dear children. It is correct. Next one. Nanotechnology is not widely used in electronics. Right? Nanotechnology is not widely used in electronics. What can you say about that? Once again, incorrect. No. In previous questions, we even discussed those things. Can you remember? It is being widely used. Actually, the size of the transistors have been reduced like up to 7 nanometers by using the nanotechnology. So it is widely used thing in the field of electronics. So it is incorrect. Nanotechnology is not a dangerous field. It's not a dangerous field. Is it correct? Actually, it is. Each and every science is somewhat dangerous, because according to the mindset of the person who is going to use it, it's going to be dangerous. Okay? There are benefits, and also if the science has been misused, then it's going to be an issue. So it's a dangerous field. Okay? It is mentioning that it is not dangerous. So therefore, that is also incorrect. So our answer should be all the above are incorrect. All of these things are incorrect. Right? Next one. Select the correct answer. So you have to select the correct answer now. Nanotechnology investigated from 1 to 100 nanometer in matter. Of course, it is correct. The first and foremost answer is correct. That's the definition for the nanotechnology now. It is going to investigate from 1 to 100 nanometers in matter. That's correct. Next one. Sri Lanka Institute of Nanotechnology is located at Colombo. Incorrect. It's at Homagama, right? Next one. Nanoscale air pollutants in effluent smoke can't be filtered. It can be filtered, right? If we can use a nano filter, then we can filter it without any trouble. That's correct. That's incorrect. Next one. Calamitous situations will not occur due to nanotechnology. Like I said in the previous question, my dear children, according to the people who are using this, according to the mindset of that people, right, it's going to change. So we can't say directly that there will not be any calamitous conditions. Okay, we can't come into direct, conclusions. According to the people who are using it, it can change. So sometimes calamitous conditions may occur in the society because of the nanotechnology. So that is also incorrect. So our answer should be the first and foremost answer. Nanotechnology investigate from 1 to 100 nanometers in matter. Right then. So we have answered 40 questions, 40 MCQ type questions, right? Now let's head on to see the next one. Right, so as usual, my dear children, you are given with the second type of question. Here you need to put a tick or else a cross according to the falsehood or the truehood of the statements. Right, let's see. Graphene is a carbon-based nanomaterial. Correct, no problem. You know that graphene is a carbon-based nanomaterial. That is absolutely correct, no problem in it. Right, it is a carbon-based nanomaterial, graphene. Next one. Diamond can be used to create nanomaterials. Diamond can be used to create nanomaterials. No, my dear children, we won't be able to utilize diamond in making nanomaterials. It's very hard and very complex. Even the bond structure is going to be very strong. So we won't be able to utilize diamond in making nanomaterials. Usually we use graphite. Okay. Next one. Serve disasters can occur due to nano armaments, right? Serve disasters can occur due to nano armaments. Correct. Because of nano military equipments, serve disastrous conditions may occur. right? If they fell into wrong hands, these nanoamendments, if they fell into wrong hands, then my dear children, definitely calamitous conditions will occur in our society. So it is correct. Next one. Fuel economic vehicles can be created with nanotechnology. Once again, correct? No. Fuel economic is very important for a certain country. Now, when you take these days, so it's because, my dear children, when increasing the population, the demand for the fuel is also getting increased. So fuel efficiency is a very important thing. So nowadays, scientists are developing different kinds of vehicles that has the efficiency of fuel by using nanotechnology. So this is correct. There's no problem in it. Next one. Favorable cholesterol can be resulted using nanotechnology. Once again, correct? No. Favorable cholesterol, that means like HDL, can be resulted by using, right, nanotechnology. Correct, no problem. Next one. Sir J. Fraser Stoddart won the Nobel Prize in 2015. Incorrect. Not in 2015, right? That is incorrect. He and other two won the Nobel Prize for making or for turning molecules into machines, right? However, not in 2015, my dear children. Okay. Next one. A DNA structure is about 200 nanometers. Totally incorrect. It's not around 200 nanometers, right? It's even more smaller than that. So it's incorrect. Sir Richard Feynman write the book Engines of Creations. Once again incorrect, right? Richard Feynman gave the speech about nanotechnology. Actually gave the speech. There's plenty of room at the bottom. He was the first person to speculate about this nanotechnology by giving out that speech, right? He didn't write a book. Next one. Wings of dragonfly is hydrophobic. Correct. Not only some dragonflies, but even in some insects, even in some beetles, we can observe this hydrophobic nature of their wings. It's because, my dear children, right, this hydrophobic nature is going to come because of the lotus effect, right? Next one. Metal gold is transparent on the nanoscale. Incorrect. Gold is not transparent. It is going to show different colors. Can you remember? Right? So, copper is transparent, however. Right? So, this is incorrect. Next one. Gold is an inert element in nanoscale. Gold is an inert element. What do you mean by an inert element? Inert means, my dear children, inactive. Gold is not an inactive element in nanoscale. It's highly reactive, way more reactive. And it is going to show different colors according to the substance, according to the size of the nanoparticles. So this is totally incorrect. Right? Totally incorrect. Gold is not an inert element in the nanoscale. Okay. Next one. Carbon has resistance-free nature in nanoscale. That is correct. Carbon has a resistance-free nature in the nanoscale. No problem. That is correct. So we have answered several questions, my dear children. We have answered like 40 MCQ type questions, and now here we discuss 12 statements regarding the regarding their truehood or the falsehood, right? So from these, I'm going to finish up this chapter. Within our next chapter, my dear children, we'll be discussing about some essay type questions regarding the nanotechnology lesson. Okay, so we'll meet with our next chapter to discuss about those questions.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.